आपका माइक ऑफ है सर।
मतलब मेरे पीछे 3 मिनट जो है ना हो जाएगा हैं। Okay, thank you. So I was actually reviewing the previous 1, 2, 3. Thank you 120 and thank you Abdul Munim, but मुझसे पढ़ा नहीं जा रहा. Okay. So I was reviewing the canal outlet, canal fall, and informed you that we have defined what is a canal fall. Canal fall is a hydraulic structure built across the canal for lowering of the bed and for lowering of the water level in the canal. And the necessity of the canal was discussed, and the necessity of the canal comes from the design of the canal. If somebody have designed the canal with a steeper slope as compared to the slope of the topography, then canal fall will be there. If we don't provide canal fall, what will happen is excessive filling will be required. And if sometime there is a sudden drop in the natural topography also, then we need to provide the canal fall. So these were discussed. Location of the canal fall was discussed, where to locate, and we discussed the location with respect to location of fall in main channel, in main canal, and in case of distributary canal. In case of main canal, because usually we don't have any off-take channels, our outlets are not there, so only the balance of cut and fill, or only the economy will be controlling the canal fall location. While in case of the distributary channel, which has to irrigate on the surrounding area, which has to give water to the outlets, then canal fall should be located on the downstream of the outlet if some outlet is nearby. Also, we achieve the economy by combining the canal fall with some other structure like bridges or some regulators in the canal. Then overall cost of both of these structure will be less as compared to providing both of them separately. So these are some of the location, and we also discussed that an engineer should also compare possibility of combining low number of falls with higher fall height, low number of falls with higher fall height. He should compare the cost of this scenario with the many number of falls with the small fall height, low number of falls with high canal fall, and many number of falls with small fall height. So its economic comparison should be done, and then it should be decided how many number of falls are necessary. Historical development of the fall was discussed: Ogi type, rapids, and stepped fall, vertical drop fall, and trapezoidal fall. And some of the falls which have been used in the last 4-5 decades in this area after 1950s or 45. These falls have been popular in this area, vertical drop and its variants. So these are the variants of the vertical drop fall. Sarda type fall, Mushtaq fall, which is a vertical drop fall, but it has a fluming. Fluming is also carried out. Usually in vertical drop fall, we don't carry out the fluming, but Mushtaq provided the fluming. So Punjab CDO fall, it has, I think, in addition to the fall, it has, but it has CDO type fall में क्या था? It has a raised crest over here. So it is a glacis type fall. CDO type fall is a glacis type fall rather than the vertical drop fall. And it also has a fluming over here. Fluming means reduction of the width of the canal. Montague fall, he provide a parabolic profile rather than a vertical drop or a straight glacis. He thought that the vertical acceleration can be can be dissipated. Vertical acceleration can be dissipated through providing a provide curved glacis instead of a straight glacis, and the curvature can be decided based upon this equation: x is equal to b into square root of 4y over g, and its I think derivation is available in the book if somebody is interested. its derivation is there in Iqbal Ali book. English type fall, straight glasses fall. In addition to that, they provided baffle blocks, baffle walls. Meter fault and non-meter faults were discussed. Those faults which can be used for measurement of the discharge, we call them as a meter fault. And non-meter fault are those faults which cannot be used for measurement of the discharges. Usually on structures, if we only measure the head above the crest, so that can be related with the discharge through the discharge equations. So measuring head, people can convert it into discharges. So many of the structures can be utilized for discharge measurement. So those are called as the metered fall. We have to start today from this topic. We need to sometime dissipate the energy. We need to sometime lose the energy within the canal, especially in case of barrages, especially in case of spillways, and also in case of canal falls. These are the similar concepts. Spillway also has to drop the water from the high water level in the dam, and it has to bring the water to the lower water levels or lower bed levels downstream in the river. But those are in the dam spillway. We call those structure in the dams. Barrages are also similar. On the upstream side, usually we have the ponded water, we have the high water level. On the downstream side, usually we have the low water level. Except in the flood condition, we have nearly similar water level condition. But in the dry condition, when gates are fully closed, huge water difference are there. And if we want to open the gates, then water will fall from the high head to the low head. Similar is the case in case of the canal fall. Usually we don't have the gates, but water level on the upstream side is higher, water level on the downstream is lower. So there is a kinetic energy developed over there. So we need to dissipate that energy. So dissipation of energy is required in case of barrages also, spillways also, and in case of falls also. So there are many devices which can be utilized for dissipation of the energy. One device is hydraulic jump. That is a hydraulic phenomena, not a structure. Hydraulic jump is a phenomena. So in addition to that, some hard measures can be taken, some hardware can be utilized to dissipate the energy, and few of them have been shown to you over here. And then in the later slides, these will be described one by one. For example, we can construct an obstruction on the downstream side all along the width of the canal. So that will be called as a baffle wall. So any obstruction in the canal, like a weir is also an obstruction. But if we make a small weir on the in the stilling basin, on the end of the stilling basin, at the toe of the fall, we will be calling that as a baffle wall. Baffle means something which obstructs the flow. So baffle wall can be of different shapes. It can be of a deflector shape, which is shown over here. It can be of a shape of more curvature is there, and water has to come back after striking this one. So we call that one as a biff wall. Or it can be open at one place and stopping the water at other place. So then we call such a baffle wall as a dentated sill. Pyramisco dentated sill. Baffle mean obstruction, wall mean wall. So it can be a continuous wall, it can be dentated wall. So Shah Muhammad want to join, and why not, he can join himself. Okay. So we need to lose the energy, we need to dissipate the energy. For that purpose, one thing is we obstruct water, and that obstruction causes turbulence, that obstruction causes hindrance, and that causes, sometimes it causes rollers within the water, and that causes the dissipation of the energy. So this deflector will cause obstruction, this biff will cause obstruction, this dentated wall is a little bit different action. This will divide the water into two layers in vertical plane. the water which is passing through this lower part of the dentated cell, you see this as dentated mean like a tooth, like a series of tooth. Like you have the series of tooth in case of saw, आरी के ऊपर जो टूथ होते हैं, तो उसी तरह ये भी there are a number of projections. So we call such a kind of wall as the dentated cell. So in one part, water will pass through the raised crest, and in one part it will pass underneath. So there will be a vertical separation of the water in two layers. So that separation of the water causes the extra turbulence and extra eddies are created, which causes the reduction of energy while water will go on the downstream side. So this is also practiced when energy is quite high. So then we use this dentated cell. If energy is smaller, only simple kind of baffle valves like deflector and drip valves can be utilized. In addition to these obstructions, sometimes we use only the bed roughness devices, or we provide some obstruction at the bed. So if we see the plan view, this is a plan bed of the canal. So we provide a block over here, block over here, block over here. So this block can be of rectangular shape. You are seeing simply the plan view. If you see it in the cross-sectional view or elevational view, you will see some figure like this. This is a triangular shaped block, but people can use the rectangular shaped block also. There's no problem. That is simple to construct, and hydraulically they have the same effect. Only the face, the flow side will be obstructing the flow. The back side is not obstructing the flow. Back side is giving it the structural stability. If there is a huge velocity, like in case of the barrages, like in case of the spillway, sometimes these concrete blocks, they are damaged, they are removed from their places, or their corners are damaged. So we have to make them very strong if high velocities are there. So these blocks can be utilized in the flow, and we use it in the falls also, we use in barrage also, and sometimes we spillways also, downstream of the spillways also. In addition to these blocks at the bottom, at the floor, sometimes we use roughness devices on the side of the canal. ये canal का cross section दिखाया हुआ है. A part of canal cross section is being shown to you over here. Half of the canal is shown, other half is not shown. On the side of the canal, they carry out the brick pitching. They line it with the bricks, and one brick is placed on its longer side, and one brick is placed on its header side. So this causes a rough side slope of the canal. So when water passes through the canal, so this extended bricks, the bricks placed on their end and bricks placed on their edges, they causes a kind of the excessive roughness, enhanced roughness is created on the side of the canal. So that also reduces the energy. So such kind of devices are have been utilized and can be used. So I have already explained that baffle wall is any kind of obstruction or any kind of the weir which is placed at the toe of the piston to serve two purposes. One is to withstand the actual impact of high velocities and to reduce those velocities, to dissipate them. And the second purpose of this baffle wall is to give some increased depth of water over here in the cistern. So that increased depth of water is sometimes required if we want to create a cushion, or if we want to place hydraulic jump, good hydraulic jump. So then higher water depth is required, and this baffle wall can help us to provide a cushion and the higher water depth. So, and this will ultimately result in reduction of energy, dissipation of the energy. So this baffle wall, if it is shape of the 90-degree turn like this over here, we usually call it as a deflector. Water will come over here, it will be objected by this deflector, and it will shoot up on the upstream side. So its working will be a little bit different as compared to the Who is requesting the control? So it will deflect the water in air through a 90-degree bend, while this will make the water swirl over here, or this will make the water go back into the cistern, and this will cause more turbulence as compared to the turbulence created by this deflector. So that is the difference. So it will biff fall will cause enhanced turbulence, or they are calling it super turbulence, will be created, and more energy will be dissipated. When the water is directed upward side, it means that will be obstructing the water coming on the down towards the downwards downstream side, and there will be more turbulence, and more energy will be dissipated over here in the cistern or in the stilling basin. This will cause water to go up, and then that water will come down on the downstream side, and by falling on the downstream side, it will it will dissipate the energy. Dentated sill, I have already explained. It deflects part of the water into in air and part of the water. So this part of the sill will work like a deflector, and this part of the water will work like a small weir. So vertically, water will be separated into two sheets of water, and over here, more turbulence will be created, and it will cause dissipation of the energy. So this is provided at the end of the system if high velocity jet persists. So relatively more energy if it is there, then we provide, rather than providing a complete wall, we provide a dentated sill if energy is more, and we don't want that all obstructed. If all is obstructed with a huge energy, then more turbulence will be there, and maybe some damage to the floor is possible over here. So that's why a part is deflected up and part is allowed to go down, and vertically they are separated into two layers, and we lose the energy in this way. Cellular or ribbed pitching. So this is carried out on the side of the canal. So keep in mind that this we are showing you the cross section of the canal over here. So a side slope is shown to you over here, and if we place one brick on the edge and one brick on the end, then enhanced friction is available, which will reduce the energy to some extent. Not as much energy will be reduced as the energy reduced by the biff wall, or by the deflectors, or by dentated sill. So if we want to lose more energy, then the more length of the canal need to be provided with the ribbed pitching. So this destroys the surplus energy downstream of the fall. Friction blocks, sometimes we call them as arrows. So they are placed at different locations. They are placed in the stilling basin, and sometimes we place them in the sloping on the sloping glasses also. Sometimes people place these blocks. So staggered, usually they are staggered. Staggered mean if one block line is placed in this way, next block line will be in between of these two blocks. So they are staggered. They are placed with a staggering over there. If a next block was placed just behind this block, so that would not be much effective. So staggering is good. That should be practiced. Staggered friction blocks are one of the most useful and simple devices to dissipate the energy. Usually their height is a quarter of the water depth over there, and the width is usually provided 1.5 to 2 times of the height. So it means if 2 times of the height is provided, the width, it means width is about half of the water depth over there. So if 1 meter height water depth is persistent over there, then 0.25 meter height of block should be there. If blocks are too high, they are not much needed. Any block part above the water depth is not effective. If block is too small, also water shoots above them, and it is not much effective. So from experiments, they have seen that quarter of the depth is suitable for dissipation of the energy. they can be of different shapes. They can be of different shapes. For example, over here we are showing you a triangular shaped blocks only. So if block shape is triangular, they are called as arrows. If block shape is triangular, they are called as arrows. Otherwise, they are simply called as friction block or baffle block. So these are the two, or impact blocks. Sometimes we call them impact block. So these three names are used: baffle blocks, impact blocks, or तीसरा क्या नाम लिया था, baffle, impact, or friction blocks. So these three names are utilized. So if their shape is like triangular, so they call it arrow. So its face facing the flow is straight. So face which is opposing the flow is same as that of a rectangular block. Only they are getting some benefit of material saving by giving it a triangular shape in the plan view. So they are saving some material over here in the planar view. So, but it will be less stronger as compared to hopefully the rectangular, because the base of that rectangular block will be larger. So it will have more contact with the underneath floor. So that will be more stronger. So it depends, if the flows are too high, the velocities are too high, maybe we have to provide the rectangular blocks over there. So people have tried other shapes also. For example, they have tried step blocks. One part of the block is of lower height, other part of the block is of higher height. So, and they have also tried blocks with the smooth corners at the side. So these sides are smooth. So those are not considered to be working good with respect to dissipation of the energy. So sharp edge rectangular or triangular blocks, these are good for the dissipation of the energy. So these were some introduction of some of the devices which can be utilized for dissipation of the energy. So mainly we can divide them into two components. One is the device in the shape of the valve, which is provided at the end of the cistern. It can be of the shape of a deflector, 90-degree deflector. It can be shape of a 180-degree deflector, which is called as biff valve. It can be shaped of one part is vertical and one part is given slope, and so we call that as a dentated. So not the whole wall is solid, but it has some opening in between. So we call that as a dentated sill, dentated wall or dentated sill. So that is one group of the devices. Other group of the devices are enhancing the friction, are providing the blocks in the floor. So friction can be enhanced at the bed, friction can be enhanced on the sides. So if we provide it on the sides, we call it as a ribbed wall. Ribbed wall is simply we carry out the brick pitching on the sides. One brick is placed on header and one brick is placed on its end, as in this way extra friction is provided. Which fall should be provided in which condition? Some guideline is provided over here. Further, you can read from the GAG, page 620, describe other kind of falls also, that this fall should be utilized in this condition. A summary of that is that if flow is less, like if flow is less than 15 cubics, which is about 500 cubics, and the 500 cubics, you can have the idea, this is that much flow which is running in Lahore branch canal. This Lahore canal, when it is passing through the Dharampura, its flow is about 450 or about 475 cubic. So you can have the idea of the about 500 cubic from this canal. So if the flow is up to 15 cubics or 500 cubics, and drop you need to provide is 1.5 or less than 1.5, then vertical drop fall, which is more simpler, easy to construct, is work sufficiently well. So this should be used. But if the discharges are high, for example up to 60 cubics, which is equivalent to 2000 cubic discharge, so then we should try to use a glacis type of the fall. Rather than providing a vertical drop, straight glacis should be provided. It should be provided with the fluming, because usually the falls, if they are constructed and bridge is also there, then the bridge cost can be much reduced if we flume the canal. Then the length of the bridge reduce, number of piers of the bridge will reduce, and in this way we can reduce the foundation also, and we can reduce the cost of the project. So if the fall height is up to 1.5 meter, but the discharge is more than 15 cubics and less than 60 cubics, then we should be going for straight glacis fall. English fall, which is I think straight glacis fall, but it has additional friction blocks on the downstream side, so that's why that is called as a baffle fall. Baffle is something which obstructs the flow. So English or baffle fall should be utilized when whatever may be the discharge, but the drop is more than 1.5 meter. If the drop is higher, we should go to the English fall, or even Montec fall can be utilized. Montec fall has a problem that its construction is difficult. The profile making is difficult. So then people don't utilize it much in this part. So English fall works sufficiently well for 1.5, higher than 1.5 meter drops. If this discharge is very small, like at the end of the canal, we have a few Q6 of the discharge, 5 Q6, 10 Q6, and we have to give a fall to the canal. So then it is recommended that well type fall should be utilized. We have not shown you the cross section of the well type of the fall. It is simply a vertical pipe in which the water fall, and then it is bent on the downstream side. You can see its cross section from the book of the Gar. So well type fall should be utilized. If the discharge is very low and high drop is there, then well type fall is necessary. So that completes one part of the lecture, introduction of the fall, which fall should be utilized where, what are the friction blocks. Second part of the lecture is components of a vertical drop fall or the Sarda type fall, and how to decide their geometry, how to decide these components. So that is the design example and the design guidelines available in the book. So this will be covered from the book of the Gar. I think 12th chapter deals with the, not sure, but 12th chapter of the Gar deals with the canal falls. So many kind of the canal fall have been designed over there. We have time only to go through the one of them. The rest you can utilize those reference material if you have to design such kind of structures in the field. So we know where to provide vertical drop fall. We know overall shape. There will be an obstruction or a wall, and there will be a cistern. So these two things are the main components of the vertical drop fall. So there are two variants of these vertical drop fall. One variant is that it has a rectangular wall which is obstructing the flow. We are showing you the cross section of the crest. So we call this part as the crest wall. So it can be rectangular crest wall, it can be a trapezoidal crest wall. If it is a vertical drop fall, which is good for a certain range of the discharge and which is good for a certain range of the fall height. When we say fall height, we means either the difference of the bed upstream and the bed on the downstream. So that is the fall height, how much bed is lowering, or it is the difference of upstream water level and the downstream water level. So that is also sometimes this head loss, or sometimes we call it fall height. So these things are fixed in case, the range of these are fixed. We have already described that if the fall height is up to 1.5 meter and discharge is up to 15 cubics, then utilize this kind of fall. So we can utilize simple rectangular crest wall if discharge is less than 14 cubics, and if it is 14 to 15 cubics or a little bit close to that, we will go for a trapezoidal shape of the fall. That is learned from the experience. So many of the formulas provided over here for design of the geometry are empirical. People have made this formula after first making these kind of the falls, and then if it is working perfectly, then they have proposed that okay, this formula can be utilized in future. So those are the empirical formula. Usually fluming is not provided in this fall. So length of the crest, which is not visible in this figure, length of the crest which is not visible, or length of the fall, will be equal to the width of the channel, width of the canal. So the whole length of the channel will be provided with the crest wall, where we have to provide the fall. And if uh, canal is rectangular, so all the width is covered with the canal with the fall crest. But if the canal is trapezoidal, then we make the canal rectangular, where we have to provide this canal fall. So at the location of the canal fall, usually the trapezoidal channel is also made as a rectangular channel. Let me show you in the figure. I think in the end there will be a plan view, if we see that one first. So here is the overall geometry of a vertical drop fall or the Sada type fall. So this is a complete longitudinal section. Here is the complete two plan view, one from the top, one from a lower location. So both of them are showing the details. So here is the canal crest, canal fall crest. Originally, the canal is coming in the shape of the trapezoid. So from the left hand side, canal flow is coming and it is trapezoid. So when we have to provide a canal fall, we give a transition to the banks with the help of the wing wall. This wall we called as the wing wall. We give a transition, we give a change to the sides of the canal, and in such a way that when it reaches to the crest, it becomes simply a rectangular channel. So यहाँ पे आके इसका shape rectangular हो जाएगा. This rectangular shape continues for certain length up to the concrete floor. जहाँ तक हमने कंक्रीट फ्लोर देना है वहाँ तक ये रेक्टेंगुलर चैनल के तौर पे चलेगी. आफ्टर दैट this rectangular shape is given a transition back to the trapezoidal shape with the help of the downstream wing wall. So this wing wall is provided on the downstream side, and then that will be embedded in the banks, and then normal trapezoidal section continues. If we see the cross section over here, AB section, so that will look like this in a rotated form. So this is cross section in a rotated form. Try to understand it. If you want to see
सॉरी
this
सर ये
rotate,
स्लाइड्स पीछे जा रही
slide पीछे जा रही है
हैं जी, लैग कर रही हैं सर.
ऑटोमेटिकली.
नहीं सर, आप लैग कर रही हैं वैसे ही. अभी ठीक हो.
Okay, 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 okay. You are not able to see this slide?
अभी शो हो रही है सर.
So I was trying to explain the construction of this vertical drop fall, and I was telling you that even if it is trapezoidal canal on the upstream side, trapezoidal channel is there, when we have to provide a fall, this shape is converted into the rectangular channel with the help of this wing wall. ये wing wall जो है इसकी shape को rectangular बना देगी. And once it is made rectangular, over here we provide a wall all along the width of the canal. So from here the message is how much will be the length of this crest. So the length of this crest will be actually the bottom width of the canal. So if the canal is trapezoidal channel, so when we convert it into the rectangular channel, so bottom widths will be protected, and over here this bottom width will be provided as the crest length. And on the downstream side also we give it back the trapezoidal shape after our concrete floor is finished. So then we give a transition back to the trapezoidal shape. So these are some of the things. So I was telling you that how to understand it. So these are the cross section at A, B, and C. A, B, and C. So left hand side is showing you the cross section over here. So this is showing that there is no trapezoidal cross section. It is a rectangular cross section. Over here, this wing wall is simply a vertical wall over here. While the section at location of the C is telling that at this place a trapezoidal shape have been achieved. So you have to either rotate your head to see it, or you have to rotate this page to see it properly. Just to save this space on the page, they have placed this cross section right in front of the plan view, so that these dimensions should match with these dimensions. So that is a way of placing drawings and rotating the figures. You should be clever enough to see them. You should be clever enough to understand them. Many cross sections have been plotted over here to make us understand it better. For example, cross section 1 1 is cross section. Here is the cross section 2 2. Cross section 1 1 is the wing wall cross section over here. So over here, deep wing wall is provided. Again, section 2 2. At this place, it will be vertical wall, but it is at a curvature over here. So then cross section 3 3 is over here. Then cross section 4 4 वो किधर है? 5 cross section 5 is here. Cross section 4 is, I think, for a toe wall. Anybody can see cross section 4? Yes, over here. Cross section 4 is after the at this location. So that is cross section 4. Okay. So coming back to start of the design concept. So we have to decide the crest shape. We have to decide the geometry of this cistern. Cistern is depressed floor on the downstream of the fall. Cistern is depressed floor on the downstream of the fall. So this depth of the cistern or the depth of the depression we have to decide, and the length of the cistern LC we have to decide. There is impervious floor we have to provide. We have to provide a concrete floor, a little bit on the upstream side and some part on the downstream side, to take care of the uplift pressure. When a fall is provided, an obstruction is provided, and there is high water level on the upstream side and low water level on the downstream side. So because of the porous media, because of the porous soil over here, water will penetrate into the soil, and it will try to uplift also this this canal bed. So if a floor is not provided over here, there is chances of piping, there is chances of seepage through this bed. So to avoid that chances of piping, to avoid the chances of the failure because of the piping, we provide a concrete floor. It is the same concept as we have provided the concrete floor in Biraj. Over there we have elaborate design because this is a small structure. So simple theory of subsurface flow will be utilized. Like it is allowed that you can utilize Bly's theory for design of the concrete floor in case of the vertical drop fall. So this impervious floor, which is not visible over here, but it should be visible. This concrete floor we need to provide. We need to decide its length. We need to decide its thickness. Two things. We need to decide how much will be the length on the downstream side, how much is the length of the upstream side. So this is the concrete floor, impervious floor we have to decide. In addition to this impervious floor, we don't immediately start the normal canal on the downstream and normal canal on the upstream side. So we provide some stone pitching. So this is same concept as in case of the Biraj. You have the pucca floor, and then you have the flexible apron. Over there they call it flexible apron. We are saying that thing over here as a downstream protection and the upstream protection. So it is normal practice that after concrete floor, you don't immediately start the normal canal or unlined canal. Rather, you give a transition. So a certain length is provided with the stone protection or the brick protection in case of the falls. So that will be provided. How much should be the length of that protection need to be decided. How much should be the length of that protection on the upstream side, that need to be decided. So these are the few things. If you are the designer of the vertical drop fall, you have to take care of these things. And most of these things have been settled down through the guidelines provided through experiments or experiences. So there are two variants. One we can be utilized for less than 14 cubics, and one can be one can be utilized for more than 14 cubics. So that is the shape. The length I have already told you, length of the crest will be equal to the width of the canal, and that is the bottom width of the canal. Because when fall is provided over there, the shape of the canal is changed to rectangular shape. Even if it is up on upstream side, it is trapezoidal, and it is trapezoidal on the downstream side. But at the fall location, we make a rectangular section over there. So whatever is the bottom width of the canal, same is the length of this crest. Length of this crest is not visible in this section. What else? The width of the crest B and the bottom width we need to decide. For example, if we take the rectangular crest first, then the bottom width should be provided, which should be nearly equal to or more than 0.55 times d under root. D, all these formulas are in SI units. Similar formulas are available in FPS system, the Nick book you have to utilize. These formula have been taken from the book of the GAR. So whenever there are empirical formulas, you cannot utilize them across the all the units. So for a certain kind of the unit, certain numerical coefficient have been utilized. So don't use it for other kind of units. So these are for SI units. So depth will be in meters. So then B will be in meters through this formula 0.55 d power 0.5. D is the height of the crest with respect to the downstream bed. D, small d, is the height of the crest with respect to the downstream bed. So if the downstream bed level is known and if D is known, so we can decide the B. Initially, when you are the designer, this B is not known. And similarly, you are designing the fall, so this D is also not known. So then either of this we have to assume and then calculate the other one and then recheck whether we have provided the correct one or not. So that will be informed to you how to start the designs problem. So both of these will not be known to you because we don't know at what level the crest should be provided. That will be making the upstream full supply level available, and that will be giving us a requirement of the H so that the discharge can pass. This nomenclature you understand, try to memorize. H, capital H is the upstream energy, total energy head on the upstream side. Small h is the water depth on the upstream side. Water depth above the crest. Total water depth in the canal is D. What water depth in the canal is D, but the water depth above the water head above the crest is small h. Capital H is total energy head above the crest. Similarly, the height of the fall is the upstream water level minus downstream water level. They are calling it downstream FSL. FSL, hopefully you all know, full supply level. When canal is running at the full discharge, we call it FSL. Then that level will be called as FSL. So the difference of the levels will be either called as HL or HF. In some formula they are using HL and some formula they're using HF. So keep in mind this is the head loss or this is the head fall height. This is the height of the fall. So bottom width of the rectangular crest, if we have decided that we will go for a rectangular crest, the bottom width which is represented by B1, so that should be dependent upon how much is the specific gravity of this fall material. So that is said to be SG, that is represented by SG, and at some places we are represented with simple S. So they said that length of the width of the crest wall will be sufficient if it is provided H plus D, which is the total head from the downstream bed. So D plus H is actually the height of the water with respect to the downstream bed. So HD, so that will be the upstream lift over here also, HD. H plus D is the pressure over here also, the pressure head over here also. So H plus D divided by the specific gravity. Specific gravity for masonry can be taken equal to 2. Specific gravity is how much something is heavier or lighter as compared to water. So concrete specific gravity is, I think, about 2.3 or 2.4. So, but if you take specific gravity of the masonry, which is close to 2, so that will give you a more conservative width at the bottom. Usually these vertical drop walls are made of masonry walls, brick walls are used over here. And if you have calculated this B, try to provide this B in the form of the number of the bricks, either two bricks or 3 bricks or 2.5 bricks, 3.5 bricks. So in these units, rather than going into the small millimeters units, try to round it off to the number of the bricks you will be providing over there. The discharge capacity, discharge formula or wear formula, which is good for this vertical drop fall, is similar to the wear formula. We know that wear formula is coefficient of the wear times length into h power 3 by 2. So this h power 3 by 2 you will be seeing in all kind of the wears, all kind of the notches. So when flow is passing over a wear or over an obstruction, then discharge is a function of h power 3 by 2. This head do affect the discharge, so that head and the width component is being taken care by this component h over b power 1 over c. So for vertical drop fall, a formula of this shape is utilized. Coefficient times length of the fall, and the length is not visible, that is perpendicular to this paper. And I told you that the length will be equal to the bed width of the canal into h power 3 by 2 into h over b power 1 over 6. So this formula can be utilized to see or to estimate the discharge passing capacity of this fall. Or if we are designing a canal, usually discharge is imposed on us. They say canal has a discharge of 200 cusics. Canal has a discharge of 10 cubics. So discharge is fixed for us, and we have to find from this formula the head required to pass that discharge for a certain fall crest width B. So we will be using this discharge formula for calculation of the head required, because other things are usually fixed. Q, L, and B are fixed in the design. Similar formula with the different coefficient is utilized for trapezoidal shape of the crest. If rectangular shape is there, so this coefficient is 1.835. If trapezoidal shape of the fall is utilized, then discharge formula is 1.99 times LH, remaining is same, 1.99 LH power 3 by 2. So discharge passing capacity for trapezoidal shape is a little better as compared to discharge passing capacity of rectangular shape. That I am saying by seeing these coefficients. Its coefficient is higher, so it means for the same head, for the same B, for the same length, trapezoidal shape fall will be passing more discharge, and rectangular shape fall will be passing relatively less. 1.385 is the coefficient for that. So these are the formulas which will be utilized for the corresponding shape of the fall of the crest. Top width, previously that was a function of the height d, that was function of the height of the crest with respect to bottom, but over here they have made it function of the total head with respect to bed. From the bed, d plus h under root, they say utilize this formula for trapezoidal crest. If we have selected trapezoidal crest, then top width should be provided at least equal to 0.55 times h plus d under root. And upstream and the downstream slope are fixed in case of the trapezoidal shape. One horizontal to 3 vertical slope should be provided on the upstream side. One horizontal to 8 vertical slope should be provided on the downstream side. So that will result into a bottom width. So we don't have a formula for bottom width. If top width is fixed from this formula, then the bottom width can be decided based upon these slopes for the location where we want to place its bottom. So usually at the bed, at the downstream bed, we place the bottom of the fall, so we can use these slopes. For example, if 1 meter is provided at the top, and we want to provide 3 meter height of this wall, so 3 into 8. So for one horizontal, there will be 3 vertical. So if we want to provide 3 meter of the height of the wall, so then 1 meter will be extension on the upstream side. While if we want to provide 3 meter over here, then extension on the downstream side will be about 3 divided by 8, uh, uh, something 0.33 will be extension over here. So top width plus the extension on the downstream side plus extension on the upstream side will decide the total bottom width of this trapezoidal shape crest. So these slopes will help you decide the bottom width, while top width will be decided based upon formula 0.55 times h plus d power 0.5. So in this way, we decide the whole crest geometry. Crest geometry is decided. Coming to the point that we don't know initially D, we don't know initially H, how to deal with it, that is described over here. So both of above these two formulas can be written in a generalized form in this way. For a vertical drop fall of any shape, whether rectangular or whether trapezoidal, we can write it in a generalized way. Q is equal to a coefficient times 2g under root times LH power 3 by 2 times H over B power 1 over 6. When this 2g under root has been incorporated in the figure, so now this formula can be utilized, I think, FPS or SI both, because this g is making the problem. If we use the value over here, so then that is fixed for particular units. For example, in SI, we will be placing G as 9.81. So then this formula with the CD 0.415, that will result into 1.835 for rectangular, and this will result into 1.99 for trapezoidal. But when G is 32.2 in FPS system, then this 1.835 and 1.99 cannot be possible. Okay, this is the generalized formula for vertical drop fall with the CD value given over here for rectangular and trapezoidal shape. Coming to the question that how to start the design for a crest, we assume a certain value of width based upon the discharges which we are utilizing, like 10, 12, 14 cubics. We utilized some value close to 2, 3, 4 bricks thickness, like 0.8 meter, 0.7 meter, 0.9 meters, things like that. We decide that this is the assumed top width of the crest. Shape of the crest we already decide based upon how much is the discharge passing through the fall. That is the discharge capacity of the canal. So if it is up to 14 cubics, we will be saying that rectangular shape is good. If it is 14 to 15 cubics, we will be saying that trapezoidal shape will be utilized. So top width we assume initially, then from the assumption of this top width, we use the discharge formula and we calculate how much H is required. In this formula or in this formula, if B is assumed, L is the bottom width of the canal, so it means we know it. Q is discharge which we have to pass in the canal, so H can be calculated. Hopefully all of you will be agreeing. So H head required to pass the discharge can be calculated, and same is true for trapezoidal section also. So if H is calculated from the discharge formula, now we calculate the upstream energy, total energy level. Upstream full supply level will be given to us. Upstream canal bed level will be given to us. So upstream depth is known to us. So upstream cross section is also known to us. Trapezoidal section is also known to us. So it means upstream flow area is with us. Discharge is with us, so we can calculate the velocity. Q over A, we can calculate the velocity. If velocity is with us, we can calculate the velocity head V square over 2G. If velocity head is with us and full supply level is with us, we can calculate what will be the upstream energy level. So when we start the canal fall design, the canal is already pre-designed. Canal is designed on the upstream side and on the downstream side. Canal sections are known, discharges are known, canal bed elevation is known, canal full supply water level is known, canal water depth is known, shape of the canal is known. So these things are pre-known to us. So we can find the velocity from that information. From the velocity, we can find the velocity head, and from the velocity head, we can find what is the upstream total energy level. If upstream total energy level is known to us, then crest elevation can be found by subtracting just calculated capital H. We have just calculated capital H from the discharge formula. So subtract the total energy level, subtract H from the upstream total energy level. You will be reaching to this level, crest level. So this crest level of the crest will be decided. Subtract from this crest level the downstream bed level, we will be getting the small d. Once this small d is known to you, then put this small d in the formula. If it is trapezoidal section, put it in over here. If it is rectangular section, put it in this formula and calculate the b. If this b is close to the assumed b, so then go ahead and continue with this provided b, assumed b or this b. If it is much different, then use this new b or a little bit adjusted b, and then recheck what is the h required and what is the crest level required and what is d. Hopefully, one cycle will bring you to the proximity that the assumed value of the b fulfills the requirement of this formula. So that is how we carry out the design of the crest elevation, design of this height of the crest with respect to downstream bed and the crest width. So these steps are written over here, and we can utilize this concept and decide the height of the crest, elevation of the crest, and the D value. So any question up till this? So this is one part, deciding the crest so that discharge can pass. So what we are seeing, what we are doing, we are passing the discharge and we are calculating how much H is required. Based upon that H, crest is being decided. Based upon this H and based upon this D, this top width is being decided. इसमें कोई सवाल है किसी का तो you are welcome.
सर डाउनस्ट्रीम बर्ड लेवल कैसे?
मैंने कहा अपस्ट्रीम कैनाल और डाउनस्ट्रीम कैनाल विल बी प्री डिजाइन. उस जब आपके पास कैनाल फॉल का डिजाइन आएगा तो आपके पास आपने ऑलरेडी डिसाइड किया होगा कि आई विल प्रोवाइड 1.5 मीटर कैनाल फॉल ओवर हियर और 1 मीटर कैनाल फॉल विल बी प्रोवाइडेड. तो अगर अपस्ट्रीम का बेड पता है तो डाउनस्ट्रीम का बेड भी पता है. इसका मतलब एलिवेशन की बात कर, जब आप कैनाल फॉल प्रोवाइड डिजाइन पे आते हैं तो उससे पहले आप कैनाल का लॉन्गिट्यूडनल सेक्शन आप डिजाइन कर चुके होते हैं. ठीक है
सर, उस हवाले से देखा जाए तो वो मतलब डाउनस्ट्रीम लेवल अप नहीं होता फ्लोर का, अगर ओरिजिनल क्लास फ्लोर लेवल को देखा जाए तो.
अगर ओरिजिनल हम ग्राउंड लेवल को देखें तो
सर उसमें डिप्रेशन ही
शुरू में क्रॉस सेक्शन दिखाया था, उस पर चला जाता हूँ आप इसके हवाले से. जब हमने कैनाल डिजाइन की तो यू हैव अ सर्टेन स्लोप. ठीक है.
यस सर.
ओके. You have drawn the longitudinal slope or longitudinal elevation of the nature topography from the contour map. आपने एक longitudinal profile बना लिया nature topography का. ठीक है. Along the alignment of the canal. आपने कैनाल की अलाइनमेंट डिसाइड की टोपोग्राफी शीट पे. वो स्ट्रेट भी हो सकती है, टेढ़ी मेढ़ी भी हो सकती है. एक अलाइनमेंट डिसाइड कर ली बेस्ड अपॉन द गाइडलाइन योर टीचर हैव गिवन टू यू. हमने अलाइनमेंट ऐसे डिसाइड करनी है कि वी विल बी ट्राइंग टू रीच टू द ऑल द एरिया. वी विल बी डिजाइनिंग इट इन सच अ वे दैट sufficient gravity should be provided. Alignment will be decided in such a way that ridge line should be occupied. So कुछ guideline we will be aligning it in such a way that inhabited area should be avoided. इस तरह की guideline आपके पास है. तो आपने alignment decide की कंटूर शीट के ऊपर, उस अलाइनमेंट के ऊपर लॉन्गिट्यूडनल प्रोफाइल आपने ड्रा करना है एक शीट के ऊपर. सो दैट इज दिस लाइन. और यहाँ पे डिफरेंट लोकेशन पे जो एलिवेशन आएगी, ये कंटूर्स आपको ये एलिवेशन बता रहे होंगे. उसके बाद आपने कैनाल का इनिशियल डिजाइन किया एंड यू हैव कम अप विद अ स्लोप व्हिच इज लेसर देन द स्लोप. पहले तो कोशिश होनी चाहिए वी शुड प्रोवाइड कैनाल ऑफ द सेम स्लोप एज द लॉन्गिट्यूडनल slope available over there. If that slope is very steep, and in many areas this is the case, if that slope is very steep, we cannot provide that steep slope. So then we will be designing the canal at a smaller slope. हम उस slope को draw करेंगे on the sheet. Then we will see where the excessive cutting is required. Over there we will be deciding, okay, I will be providing a canal fall of so much height. तो आप 1.5 मीटर की या 1 मीटर की फॉल्स प्रोवाइड करते जाएं. If you provide higher falls, 2 meter, 3 meter, then go to the glacis type of the falls. तो ये प्लानिंग आप कर रहे हैं लॉन्गिट्यूडनल सेक्शन पे. यू आर डिजाइनिंग द कैनाल लॉन्गिट्यूडनल प्रोफाइल. तो कहाँ पे कितनी फॉल देनी है वो आपने यहाँ डिसाइड करना है.
सर ये फॉल तो डिसाइड हो गया. यस सर. सर ये डाउनस्ट्रीम के ऊपर जो फॉल के ऊपर हम थोड़ा सा डिप्रेशन देते हैं नेचुरल स्लोप से.
ये हमने ये फॉल प्रोवाइड की ना, ये फॉल प्रोवाइड की. सो दिस इज द डिफरेंस बिटवीन अपस्ट्रीम एंड द डाउनस्ट्रीम. आप इसकी बात कर रहे हो, सिस्टम की बात कर रहे हो.
यस सर.
That will not matter much. This upstream, we are talking about this canal bed level. Upstream bed level minus downstream canal bed level. This is a localized depression. So we are talking water level over here will be decided based upon the canal bed over here, not based upon this cistern. Water level in the downstream side will be decided upon the bed level in the canal, not because of the few meter cistern over here. यहाँ पे वैसे टर्बुलेंस वगैरह रहनी है, यहाँ पे फॉल, यहाँ की मैं बात नहीं कर रहा. ठीक हो गया.
यस.
और वो जो डी है वो भी डाउनस्ट्रीम कैनाल बेड लेवल से ऊपर उसका वो है, क्या कहते हैं, crest elevation with respect to downstream bed level. So this D is crest level minus downstream bed level. ये downstream bed level. Okay, हम कहाँ पहुँचे थे? So we assume the B value, top width. We calculate the H from the discharge formula. We calculate the upstream total energy level. We subtract the upstream total energy level and H. We subtract H from upstream total energy level. We reach to the crest elevation over here. From this elevation, we subtract the elevation of the downstream bed. We calculate D. So this level minus downstream level, we calculate D. When D is calculated for a certain discharge, for a certain head, then use this D to calculate B from the formulas of the top width. If that is close to your assumption, go ahead. Otherwise, redo it once. Hopefully, it will be okay. Okay, now next part is design of the cistern. Cistern is said to be should be function of the H into HF.
वो hatched area के किस साइड में सर क्वेश्चन है? सर ये जो हैच्ड एरिया है फेसिंग टुवर्ड्स द बैंक ऑफ द कैनाल, सर ये भी ट्रोपोसाइडल है या ये 90 डिग्री है?
There is no bank of the canal over here. We are seeing here the longitudinal section. मुझे तो इसमें बैंक कोई नजर नहीं आ रहा.
नहीं सर, जो हैच्ड इसमें नजर आ रहा है हमें,
ये हैच है, ये हैच.
तो ये बैंक्स की,
दिस इज मेसनरी वॉल, इसी की बात कर रहे हैं.
जी जी, बैंक्स की तरफ है. तो सर वहाँ पे जो कैनाल की शेप है वो ट्रोपोसाइडल होगी या वो रेक्टेंगुलर हो जाएगी?
दोबारा एक दफा रिपीट करो. कैनाल के बैंक्स की तरफ जो है
जी, तो सर ये कनाल की शेप में कह रहा हूँ कि इधर ट्रोपोजोइडल रहेगी या इधर हम फॉर सम एक्सटेंट इसको रेक्टेंगुलर कर लेंगे।
मेरे ख्याल में बहुत सारे तुम्हारे दोस्त इसका जवाब दे देंगे। मैंने ये बात वो प्लान व्यू में जाके दिखाई थी कि इस पार्ट में रेक्टेंगुलर रहना है, इस पार्ट में ट्रेपेजोइडल हो जाना है, या यहाँ पे ट्रांजिशन देनी है। कोई है इसको जवाब देने वाला या मैं ही जाऊँ उधर?
रेक्टेंगुलर होगी।
यहाँ पे रेक्टेंगुलर होगी, जहाँ हम ये क्रेस्ट प्रोवाइड कर रहे हैं यहाँ पे चैनल रेक्टेंगुलर हो चुकी होगी। ठीक हो गया?
जी ठीक सर।
ये मैं दोबारा दिखा रहा हूँ। ये तुम्हें ये बात समझ आएगी, इस सेक्शन में से समझ नहीं आनी, ये बात समझ आनी है प्लान व्यू से। तो यहाँ से हमारा जो है ना, यूँ समझो फॉल की कम्प्लेक्सिटी शुरू होती है, ये लेफ्ट हैंड यहाँ से। इससे पीछे कैनाल नॉर्मल चल रही है ट्रेपेजोइडल लेफ्ट साइड में। ये अब आपको नजर आ रहा है ना हमारा प्लान व्यू। 49 स्लाइड नजर आ रही है आपको?
यस
ऐसे ही
सर।
है? ओके। तो ये हम जो ट्रांजिशन प्रोवाइड कर रहे हैं, यहाँ पे हम एक रिटेनिंग वाल दे रहे हैं जिसको एक कर्व दिया है, इसको हम विंग वाल कहते हैं। ये दोनों तरफ होगी, इधर भी होगी इधर भी होगी। यहाँ उसकी फाउंडेशन दिखा रहे हैं कट करके ज़्यादा इंफॉर्मेशन के लिए, यहाँ इसका टॉप व्यू दिखा रहे हैं। तो ये ट्रांजिशन ने यहाँ तक लाते लाते इसको रेक्टेंगुलर कर दिया। अगर यहाँ के क्रॉस सेक्शन देखो, 3 सेक्शन देखो, तो ये सिंपली रेक्टेंगुलर एक साइड पे, इसको क्या कहते हैं हम, रिटेनिंग वाल है, वर्टिकल रिटेनिंग वाल है। जहाँ पे ट्रेपेजोइडल सेक्शन बनना है, फॉर एग्जांपल सेक्शन सी जो है यहाँ पे, तो ये ट्रेपेजोइडल बन चुका है। और सेक्शन ए बी जो है ये क्रेस्ट है यहाँ पे, तो उसके सफिशिएंटली डाउनस्ट्रीम साइड पे यहाँ पे भी अभी भी रेक्टेंगुलर है। तो दिस रेक्टेंगुलर सेक्शन विल परसिस्ट till concrete floor is there। और कंक्रीट फ्लोर तक मेरे ख्याल में ये रेक्टेंगुलर कंटिन्यू करते हैं। जी, ये कंक्रीट फ्लोर यहाँ ख़त्म हो रहा है, तो इसके बाद जो है इन्होंने इसको रैप आउट कर दिया है, डाइवर्जन कर दिया। यहाँ कन्वर्ज हो रही है, यहाँ डाइवर्ज हो रही है। डाइवर्ज भी बेड वगैरह तो वही रहेगा, बेड विड्थ, सिर्फ टॉप विड्थ जो है उसकी शेप ऐसा ऐसा हम चेंज कर रहे हैं। ठीक हो गया? तो जो आप सवाल पूछ रहे थे वो इसमें से नज़र नहीं आ रहा था और वह मैं बता चुका था, इसलिए मैं, चलो खैर है, अल्लाह भला करे तुम्हारा। ओके, दिस इज इजी। लेंथ ऑफ द सिस्टम शुड बी एट लीस्ट a quarter of h into depth of the system should be a quarter of hf power 2/3। h is the head जो हमने पहले डिस्कस किया था, head above the crest, total energy head। कैपिटल H इज द टोटल एनर्जी हेड, टोटल एनर्जी लेवल माइनस क्रेस्ट लेवल, जो भी हमने पिछले स्टेप में कैलकुलेट भी किया। HF इज द फॉल हाइट, और दे आर डिसाइड टेलिंग यू व्हाट डू यू मीन बाय HF। HF मीन अपस्ट्रीम वाटर लेवल माइनस डाउनस्ट्रीम वाटर लेवल, और अपस्ट्रीम बेड लेवल माइनस डाउनस्ट्रीम बेड लेवल, बोथ विल बी होपफुली सिमिलर। And length will be 5 times of this product H into HF under root. So this much length should be provided. So this will be called as LC. ये चीज़ें decide होगी। Third thing is how much should be the length of the concrete floor, impervious floor, design of the impervious floor. So as I already told you, this will be depending upon the length of the concrete floor should be depend upon the fact that when water comes out, the gradient, the head gradient H over L, यहाँ पे अब H की definition a little bit different है as compared to the H definition previously। यहाँ पे H हमने क्या define किया था? Previously H was defined as the water depth above the crest। तो note it कि यहाँ पे H is again defined but it is different। H is head causing seepage। So when fall is working with the full supply discharge, then head across the fall which is causing seepage is upstream water level minus downstream water level. इन दोनों का जो difference है, that is the differential head, or that is the unbalanced head which is trying to cause the seepage. वैसे तो अगर मैं यहाँ पे डाउनस्ट्रीम पे फर्स्ट किया, यहाँ तक मैंने फ्लोर दे दिया है, तो यहाँ पे अगर सीपेज में बाहर निकलना है तो यहाँ पे इस पे जो प्रेशर लग रहा होगा, दैट विल बी दिस ग्राउंड लेवल, दिस बॉटम लेवल एंड द डिफरेंस ऑफ द वाटर लेवल ओवर हियर. ये टोटल जो है हेड जो है ये यहाँ पे इसको अपलिफ्ट करने की कोशिश कर रहा होगा. तो हेड ग्रेडियंट इज दिस डिफरेंशियल हेड divided by the length of the up till that point. So at the exit point जहाँ पे इससे निकलना है, this gradient should be, this head causing seepage gradient should be less than or equal to 1 over C, where C is the Bligh's coefficient. और ब्लाइस का कोफिशिएंट हमने उधर जब बिराज के सबसरफेस फ्लो वगैरह पढ़ रहे थे, फॉर डिफरेंट मटेरियल, ये चैप्टर 3 इकबाल अली से मैंने लिए ये टेबल, फॉर डिफरेंट मटेरियल required C value is given. For example, for coarse sand, C value should be 12 or more than 12. So if the gradient of the head causing seepage is less than 1 over C, we say that with respect to uplift pressure, this structure is safe. So total length of the impervious floor is determined by subsurface flow theories, जो ब्लाइस भी है, लेंस भी है, खोसला भी है. अगर आपने इसको मजीद डिटेल में करना है तो यू कैन गो फॉर खोसला थ्योरी, वरना वर्टिकल ड्रॉप फॉल में सिंपल ब्लाइस थ्योरी इज कंसिडर्ड टू वर्क सफिशिएंटली विद अ सेफ डिज़ाइन. सो सी हम मटेरियल के हिसाब से जो सॉइल मटेरियल यहाँ होगा, वी विल टेक सी फ्रॉम द रिकमेंडेड टेबल्स. Putting this C value over here, we can calculate L against a certain head causing seepage. इसी इक्वेशन से H over L should be less than or equal to 1 over C can be written as L should be greater than or equal to C times H. इसी को हम दूसरे तरीके से लिख सकते हैं कि the length should be greater than or equal to C times H. C we will take from the table with respect to different material are in that place. यूजुअली हमारे पास यहाँ पे फाइन सैंड और फाइन सैंड एंड सिल्ट होती है, तो 18 इज द ब्लाइस कोएफिशिएंट, और फाइन सैंड होती है तो 15 इज द ब्लाइस कोएफिशिएंट. तो 15 टाइम्स हेड causing seepage. तो head causing seepage can be different in different condition of operation of the fall. When canal fall is working with the full discharge, फिर H will be upstream full supply level minus downstream full supply level. ठीक है? When canal is working with the full capacity, so this is the case. When canal is closed and the water level is standing up to the crest level over here, although we provide a mechanism that some holes should be provided and water should not kept on standing over here, assuming those holes are closed, then water is standing up to the crest level and there is no discharge passing over the crest, and there is dry bed on the downstream side, then H will be this crest level minus downstream bed level. When canal is closed and there is no water on the downstream side, then H will be the crest level minus downstream bed level. इन दोनों में से जो sphere हो, that will be the utilized for design of the length of the floor for this fall. Out of this floor length, some part will be provided on the downstream side, some part will be provided on the upstream side. So that will be decided based upon minimum, the downstream length of the floor should be height of the fall plus 2 times depth of the water on the downstream side plus 1.2 meter. So जितने downstream पे depth है पानी की, उसमें 1.2 मीटर या 4 फुट के करीब ऐड कर दें, multiply by 2 plus height of the fall. This much length should be provided from the crest on the downstream side, this length of the downstream floor. It has nothing to do with LC. Usually LC will be smaller, this will be larger. So out of the total length which we have calculated from the Bligh's theory, this LD should be provided on the downstream side, remaining should be provided on the upstream side. So that is the balance flow length should be provided upstream side. So that is easy. So once you have provided the floor length have been decided, next thing is thickness of the floor. Thickness of the floor is decided based upon the upstream pressure which is caused by this seepage water. And we assume that upstream pressure of the floor, and at the end of the floor there is upstream pressure is reduced to 0. So thickness will be decided in SI units. On the downstream side, it will be at least 0.3 meter will be provided always, wherever pressure head or seepage head is not requiring any thickness, even then 0.3 meter will be provided. So 0.3 meter plus head causing seepage, which we have already discussed previously, head causing seepage, divided by G into L divided by GL multiplied by X. X is the distance from the downstream edge of the downstream edge of the concrete floor. For example, over here concrete floor is shown to you. So from here X will be 0. As we go up, X will enhance, and over here it will be X will be equal to LD. So when it will reach to over here, so then we will be requiring the maximum thickness will be required at the downstream edge of the crest. So same thickness will be provided in some length on the upstream side, and then a minimum thickness will be provided 0.3, 0.4 meter will be provided on the upstream side. Theoretically, no thickness is required to take care of the uplift pressure over here, because whatever is the water creating the pressure over here, same water is pushing it down also. So uplift pressure is 0 on the upstream side. So we are providing this as a factor of safety only. So minimum 0.3 meter is provided as the upstream, 0.3 to 0.4 meter is provided on the upstream side, and on the downstream side thickness will be calculated at different X value. At 2-3 different X values, this thickness will be calculated to economize the project. Otherwise, the maximum thickness will be required just underneath the downstream face of the crest. यहाँ पे जो है maximum thickness इसको चाहिए होगी. So if we keep X is equal to LD divided by L multiplied by H over G, that will give you the maximum value of this. No need to calculate this T using this formula on the upstream side. कोई भी बंदा x को L तक ले जाए तो उसके T value quite high आ जाएगी, but our concept tell us that there is no uplift pressure on the upstream side, because the water standing over here balance the uplift pressure, so we don't need to provide thickness of the floor to take care of that uplift. On the downstream side, because water standing over here is not same as the uplift pressure over here, so we need to provide a thickened slab over here so that the uplift pressure can be taken care by the weight of the floor over here. Same concept you have utilized in barrages. In barrage, there are two concepts for designing the floor. In barrages, there are two concepts for designing the floor. One we have taught to you in the lab part, to design the floor of so much thickness that the uplift pressure is balanced with that. So that is the same concept as it is given over here. Another concept is design the floor as a RCC slab over there, in which the piers are taking that load. So वहाँ पे हमें RCC slab देनी पड़ती है. Then we have to design that slab as an RCC slab. Over here we don't have to provide an reinforcement as a flexural reinforcement. Only maybe the shrinkage and temperature reinforcement will be sufficient in this concrete. So over here thickness of the slab is decided based upon the uplift pressure. While in case of the RCC slab, which take care of the flexural also, over there the piers will also be supporting the slab, and then we need to provide some flexural steel over there also. So some of the barrages have been designed using that concept. In that case, more steel will be required, but less thickness of the slab will be required. So these two concepts have been utilized in case of the barrages. But in fall, we don't need to go to the RCC design of the floor. This this is a small structure, so we provide the thickness which is balancing the uplift pressure, and we add some factor of safety into it. So at least 0.3 meter will be provided even if the thickness is not required. So upstream side 0.3 meter or 1 foot slab is placed. On the downstream side, thickness is calculated using this formula. Okay, so that is how we decide the length of the floor. We decide the thickness of the floor. इस part में कोई question है?
Sir, what is G in formula?
G वही है, specific gravity है. वहाँ पे SG बोल दिया था, यहाँ पे G बोल दिया. G is the specific gravity of the concrete, and usually in fall we take it 2.3 or simply we take it 2. I think इसको 2 लेना है. ठीक है? Specific gravity of the material utilized because its weight is taking care of uplift. अगर H pressure है यहाँ पे, ठीक है, प्रेशर हेड है, अगर 1 मीटर स्क्वायर एरिया है तो आपको न्यूटन्स मिल जाएंगे अगर मैं एरिया से मल्टीप्लाई कर दूं. तो दैट विल बी द फोर्स व्हिच विल बी ट्राइंग टू पुश इट अप. H इज द हेड काजिंग सीपेज और अपलिफ्ट प्रेशर हेड. 1 मीटर स्क्वायर पे H into 1 meter square, that will be so much Newton of force will be lifting up. How much will be the thickness required to balance that one? That will come from this unit weight of that material. Got it? So unit weight multiply by the unit weight of the water. So specific gravity multiplied by the unit weight of the water. So that will give us the unit weight of the material. Specific gravity multiplied by unit weight of the water gives us unit weight of that material. So unit weight of that material multiplied by the same area 1 meter square will give you how much is the weight of that material. So they are balancing each other. So you can see its derivation is available in the book, how they have reached to this formula. So uplift pressure is actually balanced by the downward load of that material in 1 meter square area, and in this way thickness is decided. In addition to that, this is factor of safety added 0.3 meter into it. Okay, so that's if x increases. So if x is 0, actually we don't need the right hand side. When x is 0, so this part will become 0. Only 0.3 meter will be the thickness provided. So over here 0.3 meter will be provided. So for us 2 or 3 steps we will be choosing x value, and we will be calculating the thickness in 2-3 steps. Over here maybe after 1 meter or 2 meter of x we calculate t again, and then provide that much thickness. Again we calculate close to over here and then provide thickness over here. So that is how the transition or changes in the thickness are visible over here. Maximum thickness is over here. One option was provide the same maximum thickness throughout the floor. That will be an uneconomical option. So decide it based upon different lengths and give it a transition. In case of barrages, this thickness becomes too high. Sometimes 12 feet, 13 feet की thickness slab provide की जाती है. चश्मा barrage में तकरीबन 10-12 feet की I think provide की हुई है thickened slab just to take care of the uplift pressure. While in case of over here in falls, you will be calculating, I think it will be few meters. Okay, so floor is finished, crest is finished, cistern is finished, floor is finished. Now remaining is the transitional part, the downstream protection and the upstream protection and the protection on the sides. So first we take care of the downstream protection part. These are the additional protection after concrete floor is finished. So these protection are provided and on the bed, and these protection are provided on the sides. So the bed protections are usually, in case of the vertical draft wall, two brick thickness are about 20 सेंटीमीटर. ये इसने गाग में 20 सेंटीमीटर लिया है. अगर हम 9 इंच की थिक ब्रिक को समझें तो that will become I think 22 सेंटीमीटर थिक brick pitching is provided on the downstream side for a length as given by this table. उस पिचिंग की लेंथ कितनी होगी वो इस टेबल से हम डिसाइड करेंगे. So this brick pitching will be provided over the brick ballast of 4 inches or 10 centimeter thickness. So downstream पे protection after the concrete is finished, we will be providing 2 brick or 9-inch thick brick pitching over the ballast, 4-inch thickness ballast. And its length should be taken from the table, or at least it should be 3 times the depth of the water on the downstream side. जो downstream की depth है, for example 1.5 meter depth है, तो 4.5 meter length पे हम bed की pitching करेंगे at least. But if head is more, for example head over the crest is, let us say, is about 1 meter, so then 13.5 meter plus 2 times of the canal fall height. So this much will be the length of the downstream bed protection. So depending upon the head above the crest, if head above the crest is just a foot or 0.3 meter, then 3 meter pitching is sufficient. Downstream brick pitching is sufficient. If it is about 1.5 meter, then 22 meter plus 2 times of the fall height is required. So that is how we decide the downstream protection. In addition to this, we need to provide some curtain walls. So these are the curtain walls. So at least 2 curtain walls are always required, one at the end of the concrete floor, one at the end of the pitching. But more curtain walls will be required when this bed pitching is longer. So that is mentioned over here. At least one curtain wall will be required at the end, up to head of 0.9 meter. But when head is more than 0.9 meter, 2 curtain wall, and when head is more than 1.2 meter, 3 curtain wall will be required. And this tells you how much should be the depth of those curtain walls. On the downstream side, the bed is given a slope of 1 in 10. Slope is provided on the downstream side, sloping at 1 to 10. The bed is given a certain slope on the downstream side. So that will be visible from this figure. So this is the longitudinal section. So this is a bed pitching provided. The last part of this pitching is given a downward slope of 1 into 10. And then the last curtain wall will be provided over here. And then the normal bed will be located over here. So this is the detailing of what we call it vertical drop or Sarda type fall. The side pitching will be provided to certain length after the warped wall has been finished. After this warped wall has been finished, and this warping have been done from the end of the concrete floor up to certain length. So this downstream pitching, upstream pitching, side protection. Side protection will be provided on the both side of the canal, so that the side should be protected in the initial part, and then it will be terminated by giving an angle of 45 degree. At an angle of 45 degree, it will be finished. It will not be finished vertically. Downstream wings are kept vertical for a length of 5 to 8 times of HHF under root. तो ये vertical रहेंगे 5 to 8 times. So this wing walls will be vertical up to 5 to 8 times of HHF under root from the crest. So उसके बाद then they will be warped out to give a gradual transition. They should be taken up to end of the Pakka floor. Wing wall must be designed as a retaining wall. All these wing walls are designed because on the one side it is water, on the other side it is soil over there. So to take the soil pressure over there, so these should be designed as the retaining wall, subject to full pressure of the submerged soil at their back when the channel is closed. For such wall, base must be kept equal to one third of its height. So just a guideline के base width should be 1/3 of the height of the wall. So upstream protection, similar to the downstream protection, there are upstream protection are required, which include wing walls, which include bed protection, and how many curtain walls will be required on the upstream side. So upstream wing walls will for rectangular crest, if the crest is rectangular, then we can provide upstream wing wall at 45-degree angle. Simply a 45-degree angle is given to the wall, and it embeds into the embankment of the canal by 1 meter. If it is a trapezoidal or more discharge is there, then a curved wing wall is provided on the upstream side with a curvature of at least equal to 5 to 6 times of the head. So ये guideline आपको दे देंगे. It will help you decide this curvature 5 to 6 times of H, and this curvature should extend up to an angle of 60-degree. So after that, a straight wall will go into the sides, and it will be embedded into the berm or the embankment by 1 meter. So that is upstream wing wall. Upstream protection is provided brick pitching in the length equal to upstream water depth. So ज़्यादा लंबी brick pitching नहीं चाहिए upstream side पे. On the upstream side, this brick pitching is required equal to the depth of water over here, and it is given a slope of 1 to 10 also. So in addition to this, upstream curtain wall is provided. So a curtain wall will be required over here for floor, concrete floor also, and for this brick pitching also a curtain wall is provided. Upstream curtain wall is provided having a depth of 1/3 of the water. So these are some of the things which we have to decide. In addition to these cube blocks, or these blocks will be provided in Sarda type of the fall with a height of 0.2 meter, 0.2 meter width, and 0.2 meter depth to dissipate any excessive energy available over there. In addition, there will be some weep holes will be provided over here, so that if any standing water is there, that is drained out. Holes will be provided over here. So that is how, and then we propose a drawing, and then this drawing is given to the field to construct it as per drawing. There is a design problem which you have to solve yourself and then submit it. There is you have to design a Sarda type fall with a fall height of 1.5 meter. Design a 1.5 meter Sarda type fall. So this is actually the fall height. Having a discharge of 12 cubics with the following data. Bed level is given, upstream bed level. Similarly, downstream bed level is given. So this is matching with this fall height. 103 minus 101.5. Difference is 1.5 meters. So sometimes we don't give you this fall height. We only give you the bed elevation. So you should be clever enough to find the fall height yourself. Or we only give the full supply level upstream and full supply level downstream. So difference of that will also tell you the fall height. So design a fall height, fall with a height of 1.5 meter and 12 cubics discharge. So rest is the side slope of the channel. There is a trapezoidal channel available with a side slope of 1 to 1. And what else? Bed width is given for that channel as 10 meter. Bligh's coefficient for carrying out the concrete floor calculation, C, is given as. Sometime we will be giving you only the material type. We will be saying fine sand is there, and a table will be provided, or it will be either direct C will be given or material type will be given to you. So C you will be selecting from the table then. So same concept which I have just given to you. Initially they have assumed a value of B. So length of the crest is bed width of the canal, 10 meter. B is assumed 0.3 meter because it is 12 cubics, so it is a rectangular shape is selected. And then using this formula, assuming this B, H is calculated to be 0.76 meter. Then velocity is calculated from the discharge and the shape of the channel. Area of the channel is calculated from the trapezoidal area formula. Discharge divided by area gives the velocity of approach. VA is velocity of approach. And using this velocity of approach, velocity head is calculated, V square over 2G. Then upstream energy level, upstream full supply level plus velocity head. Then reduced level of the crest is created, upstream energy level minus H. and using this reduced level, D is calculated, crest level minus downstream bed level 2.27. Then they have put it in the formula. B comes out to 0.825, which is more than 0.8. Therefore, we will be rechecking it at least once. We will be providing a width nearly equal to 0.85 or 0.825 or 0.84. A guideline is if you are providing bricks of 22 centimeter, 0.22 meter, 0.229 meter ये होता है ना 9 inch. So if you are providing bricks of 0.229 meter, so it should be multiple of that. So see if 4 bricks are sufficient for this or 3.5 is sufficient for this. So that value should be selected. A little bit larger or smaller will not matter much. So that value should be selected over here, and then recheck the H, recheck the D, and then recheck the B from this formula. Hopefully more close value will be there. I think we can ignore a difference of something 0.1 meter के आसपास difference हो तो we can ignore it. That is just my understanding, not written anywhere. Shape of the crest, as it has been informed, the base width will be H plus D over the specific gravity 2. So bottom width will be 1.5 meter. Design of the cistern X and LC using these two formulas have been given. X comes out to 0.27. They have rounded to 0.3 meter. This depth is 0.3 meter. 1 feet depth is provided. Length is about 5.5 meter from this formula. Length of the impervious floor for C 7.5. They have calculated to be 17 meter is required. H is the head causing seepage. So a minimum length on the downstream side comes out to be 7 meter. So 7 meter will be provided on the downstream side out of the 17 meter. Rest will be provided on the upstream side. And so remaining is thickness you calculate using the formula yourself. T is equal to 0.3 plus H over G into X over L. So उससे आप different location पे T calculate करें and then make the drawing. Then decide the downstream bed pitching, downstream side pitching, how many curtain walls are required on upstream side and the downstream side. That completes the design. So please complete it and submit it as an assignment if possible. Not compulsory, but please do it, must do it, because usually either we ask to solve a problem from the outlet or from the fall. So these are usually we ask it in either midterm or end term exam. तो इसको अगर आप एक दफ़ा हाथ से काम करेंगे तो you will be able to do it in exam, otherwise difficult. So if you have any question in this part, you are welcome. 120 सो गया क्योंकि उसका वो चला गया उस पे ऑन होल्ड पे चला गया. Okay, I take a attendance now, and then we start the next part of the lecture, that is the concrete lining. Attendance. If you will be able to design a vertical drop fall or not with this background, हो जाएगा. कोई भी नहीं कह रहा हाँ जी हो जाएगा.
सर क्या चीज?
वर्टिकल ड्रॉप फॉल डिजाइन कर लोगे जैसे आप लोग बीम डिजाइन कर लेते हो, स्लैब डिजाइन कर लेते हो. वर्टिकल ड्रॉप फॉल डिजाइन कर लोगे. अगर कोई बंदा यही कहे 14 क्यूबिक्स के लिए 1.5 मीटर की फॉल है, वर्टिकल ड्रॉप फॉल की मुझे ड्राइंग दे दो, बना लोगे? नहीं
बना लेंगे सर.
पेपर में बनानी पड़ेगी.
कॉन्फिडेंस नहीं आ रहा. रीजन इसके कंक्रीट के जब आप डिजाइन कर रहे होते हो तो आपके पास जितना टाइम होता है, कई बीम्स आपने डिजाइन किए हुए होते हैं. यहाँ हमारे पास वाटर के सब्जेक्ट्स में टाइम इतना थोड़ा है कि जस्ट ये इतना टाइम दिया कि एक फॉल ही आप डिजाइन कर सको. सब्जेक्ट्स कम है वाटर के एज कम्पेयर टू कंक्रीट, तो इसलिए इसको आप एडिशनल टाइम खुद से आपको देना पड़ेगा. ओके, आई हैव पुट द अटेंडेंस इन द व्हाट्सएप ग्रुप. CR is requested, 120 is still sleeping on hold. इसका कौन है दोस्त करीबी जो जाग रहा है इस वक्त? 121.
सही. गांव में रहते तो उसके नेट की कभी कभी प्रॉब्लम हो जाती है.
नेट की प्रॉब्लम में होल्ड में नहीं जाता, वो लॉग आउट हो जाता. वकील तेज है इसका. होल्ड में उस वक्त जाता है आई थिंक कि जब आप इसको काफी देर तक माउस को हिलाएं ना, ऐसे ही ना.
नो सर, जब आप मोबाइल पे क्लास ले रहे हो और आप मिनिमाइज करें तब होल्ड पे जाता है सिर्फ. सर माउस के हिलाने से नहीं करता.
जब आप मोबाइल पे क्लास लें और फिर आप इसे मिनिमाइज करें. अच्छा, तो वो भी वही एक ही बात है, यानी आप कुछ और काम कर रहे हैं. गुड. ओके, नेक्स्ट पार्ट, बिकॉज मेरे ख्याल में मेरे पास 2-3 चीजें हैं which I will not be able to finish next time also, so I will ask you to go through those lectures yourself. For example, I have to cover canal lining. Varabandi have been covered in the lab part, I think. Is it so? आपको वाराबंदी की असाइनमेंट दी है उन्होंने? कोई नहीं बोल रहा. Have you carried out?
जी सर, वो कैनाल डिजाइन में चल रहा
है.
जी सर, कैनाल डिजाइन में सारा कर रहे हैं, आउटलेट और वाराबंदी सारा.
हाँ, वाराबंदी मेरे ख्याल में लैब में कर लिया, तो मैं यहाँ नहीं कवर करूँगा. एक मेंटेनेंस ऑफ द कैनाल है, कैनाल लाइनिंग है. So I will try to cover it in I think 1 hour lecture will be available to me next week. So उसको थोड़ा सा एक्सटेंड करके I will try to cover this thing. आज मैं ये 10 मिनट और ले रहा हूँ, आपके कैनाल लाइनिंग शुरू कर देता हूँ ताकि नेक्स्ट टाइम ये फिनिश हो जाए. Here in this section you see a lined canal under construction. इसमें तस्वीरों से कुछ समझाने की कोशिश की जाएगी, और you see the construction method of the lining. वो ज़्यादा इंटरेस्टिंग है. Lining is simply some artificial material to cover the prism or the what we call it perimeter of the canal. Prism of the canal को अगर हम किसी artificial material से cover कर दें, not with the other material, artificial material like concrete or किसी भी impervious material से cover कर दें, we call that as a lining. So if that is concrete, we say this is concrete lining. तो ये यहाँ पे इन्होंने एक वो बनाया हुआ है, क्या कहते हैं, फॉर्म वर्क, which help them. अभी तो ये कैनाल लाइनिंग कर रहे हैं बॉटम पे. साइड कैनाल लाइनिंग इज बीइंग डन ओवर हियर, बैकग्राउंड पे जो आप देखेंगे. तो साइड पे जो लाइनिंग है वो यहाँ पे हो रही है, तो बॉटम पे कैनाल लाइनिंग है वो यहाँ हो रही है. तो they usually have the slip form work. ये form work के खास टाइप है, which roll ahead once it has carried out the work at one place. एक पैनल जब इसने प्लेस कर दिया होता है, इसको फॉर्म दे देता है, तो then it roll to the next place. Rather than हमारे जो simple form work होते हैं उसे हम strike out करना होता है और फिर दोबारा से लेकर it moves to the next place. They are mounted on the wheels on some structure which is easily to move from one place to other place. When you have to carry out the work on a longer dimension structure like the lining, like you have to construct the parapet of a road, तो फिर आप slip form work is a good thing. So ये slip form work is being utilized over here, and they are providing the material with the help of the concrete mixer. It means they have a concrete mixing plant somewhere, or from there they get the concrete, ready mixed concrete, they place it. So this slip form will give it a proper shape, compact it, and then move ahead. So this is how usually a large project lining is carried out. मैं लाइनिंग के अंदर जाने से पहले मैं एक तो लाइनिंग की वीडियोस अगर आपको दिखा दूं तो योर इंटरेस्ट विल बी डेवलप्ड. यहाँ पे ये कंक्रीट लाइनिंग ह्यूज स्केल पे हो रही है. स्लिप फॉर्म वर्क्स आर बीइंग यूटिलाइज्ड. मैं देखता हूँ अगर ये वीडियो चल जाती है। Cannot open the specified file. Cannot open the specified file. Let me go into the file location. यहाँ पे कोई वीडियो की फाइल नजर आ रही है?
नो सर।
यहाँ पे कोई भी नहीं है। ओके, तो YouTube जिंदाबाद। कैनाल लाइनिंग सर्च करो YouTube पे, you will be seeing many videos how to carry out the canal lining at a big project. मेरे पास थी यार, ये लाइनिंग है। हाँ, ये आ गई। Semi mechanized lining paver slip formwork concrete lining, open with VLC media player. ये मैं जरा फास्ट करके दिखाऊंगा। पेवर है, जैसे आपका पेवर्स होते हैं रोड्स कंस्ट्रक्शन, इसी तरह ये लाइनिंग कर रहे हैं। They are feeding the concrete underneath with the help of this helical screw. तो ये अभी फ्रंट साइड ही है। बैक साइड में हम देखेंगे कि it will give it a shape. They have the control for levels and the sides, so sensors वगैरह लगे हुए होते हैं। They can place within the expansion joint, they can place the steel bars automatically. जहाँ पे expansion joints हैं वहाँ पे steel bars provide कर देते हैं। So this is the back side. So over here they have a plain formwork, so that makes the lining the perfect shape on the back side. ये इसके edge को control करने के लिए एक वीडियो है। This is the final shape. इसी तरह की और जो वीडियो हैं लाइनिंग पेवर, ओपन विद वीडियो। ये साइड पे लाइनिंग करने के लिए ये रोलर है विच मूव्स अप एंड डाउन, moves up and down and then moves in the longitudinal direction, so that जहाँ से बेहतर नजर आएगा मैं वो दिखा। ये they have a roller which is supported on a frames on a truss, and it is being lifted or it is being pulled with the help of the ropes. ऊपर पुल किया जाता है, फिर अपने वेट से नीचे आ जाता है, इससे ये लाइनिंग की शेप मिल जाती है। इट इज़ बीइंग फेड मटेरियल एट द बॉटम, नीचे जो है ना इसका मटेरियल जो है ये बेस है। यहाँ पे आई थिंक मटेरियल ये कोई हेलिकल स्क्रू टाइप की चीज़ है जो इसको फीड करती है। these are being practiced। तो ये एक पैनल कंस्ट्रक्शन के बाद ये पूरा फॉर्म वर्क आगे मूव कर जाएगा। ये मूविंग ऑन रेल्स, ये टेम्परेरी रेल्स लगाई हुई हैं। ये एक लाइनिंग की इस तरह के आपको गाजीपुर की शायद मिल जाए, लेकिन तो बैकग्राउंड दिखाने के लिए ये गाजीपुर की कंस्ट्रक्शन है। गाजीपुर इज अ चैनल नियर करबेला। इसमें इतनी अटैक नहीं नजर आ रही। So you can see similar methods of lining. So this is semi mechanized, उसमें पूरा slip formwork यूज हो रहा था। यहाँ पे अगर छोटी कैनाल का प्रोजेक्ट है, you can place a few laborer at the top and they can pull the rollers up and down. तो ये एक semi mechanized। यहाँ पे ये at the back of concrete lining, usually we have to take care of the pore water pressure. तो उसको ड्रेन करने के लिए हमें ड्रेनेज प्रोवाइड करने पड़ती है. तो ये होपफुली ये ड्रेनेज पाथ प्रोवाइड कर रहे हैं सो दैट वाटर कैन बी ड्रेन्ड आउट ऑफ दिस प्लेस. पोरस मटेरियल यहाँ पे प्लेस करके या फिर पाइप के ज़रिए से पानी इसको निकाल लिया जाएगा. They are putting it to the optimum moisture condition so that the compaction should be done in a good way. अब ये वही मैकेनाइज्ड वे पे आ गए. So this is how lining is carried out at larger products. ये इसकी क्यूरिंग को रिड्यूस करने के लिए इसको केमिकल के ज़रिए से स्प्रे किया जा रहा है so that the curing needs can be reduced. Otherwise cracks will be there. So ये पूरा प्रोजेक्ट इन्होंने स्टार्ट से कर दिया. Sometimes we use geomembrane instead of concrete lining. Geomembrane are utilized. These are the synthetic material of PVC or other materials. So they are utilized like clothes, like a lining of the clothes over there. ये उसको दिखाया हुआ. We have to give sometime the क्या कहते हैं connection बनाना पड़ता है. ये उसका overlapping and connection have been provided. They are making a storage pond and they want to reduce the seepage. They have given a geomembrane lining over here. For this canal, they have provided the geomembrane lining. Their problem is usually the puncturing of this geomembrane lining. अगर ये puncture हो जाए तो then seepage शुरू हो जाती है. तो that we have to take care. If we have to give a connection, so sufficient overlap should be provided and sufficient adhesive should be placed over there so that it can be should not give way to the seepage. They are giving you a different project over here. They have to utilize the lining. So हमारे भी एक concept ये है कि we should provide reservoir or storage close to the farmland so that if some farmer has excessive water available, he should be able to store water in the reservoir of his own and he utilize it whenever he need it, whenever he needs that water. ये what we call it farmland reservoir concept they are showing. Usually reservoirs close to the farmland. So to give you a quick review of the lining. Simply lining is artificial material. Lining is the protection of the canal prism with the impervious material, and it can be rigid like concrete. It can be semi-rigid or flexible. Sometimes we use clay puddle. We use sometimes clay lining also. That is the cheapest lining. So that can also be, if it is impervious, then we say this is lining. Purpose of the lining is minimizing of the seepage, avoiding waterlogging, and enhancing the capacity of the canal. So we will go through this in the next lecture. And thank you very much. 10 o'clock is already there, and 10 students have already gone because attendance was taken. Okay, Allah Hafiz. Stop recording.